Okay, now we're going to uh, discuss the test for hardenability, known as, again, the Jominy in Quench test for hardenability. Now, what I've drawn here is just sort of a little schematic of what's taking place, and this red piece here, this kind of T-shaped piece, is the actual test specimen. It will be a 1-inch standard test specimen size is a 1-inch diameter piece of steel. It'll be 4 inches long, and it'll have this head on it so that it won't slip through this fixture, this green fixture that's just holding it in place. Now, it's holding this specimen in place, and down here at the bottom, just below the end of this, there is a water nozzle. All right, and this water nozzle is placed so that, and the velocity of the water coming out here, so that when it's turned on, the water just hits the end of the specimen, not the sides. So it'll just trickle off and hit the ends of the specimen and not drench the whole sides of this thing. So that's how that works, and the water will be roughly 75 degrees. Okay, so now the specimen would have previously been heated in a furnace to just above its austenitizing temperature, where we do a complete transformation into an FCC lattice structure, and then it is immediately taken out of that furnace and then put into this test fixture, again, that suspends it above this little water nozzle. And I've got kind of sort of, it's not exactly a sample, an ASTM sample, but it kind of simulates what we're talking about here. Here's a piece of steel. This is actually 4 inches in length. All right, and this is actually a forging of a fastener before it gets finished. But it looks kind of like this T-section right here from here down. Now this happens to be about 3/4 of an inch in diameter, but anyway, you kind of get the picture for what this kind of looks like. So, and then I actually found sort of a little nozzle, water nozzle, and so it would look something like this. This water nozzle would be placed right below there and then turned on, so that just this bottom section of this piece would be getting wet with water cooling down, in other words. So that's kind of what this apparatus looks like. Okay, so that stays on there for about 20-25 minutes or so till it's completely cooled down, and then we take it, and what we do is what originally was that whole length was, of course, completely round. So now what we do is we take that round section and we flatten it off and put a little flat spot on it, the full length of that. So essentially what we do is just, and I'm going to exaggerate, but we just put a flat spot on that like that. So now this whole piece is going to have a flat spot, kind of like this. All right, and on this flat spot, we're going to make hardness tests. And we're gonna do these hardness tests every 1/16 of an inch, starting from this end, and this is the quenched end here. The quenched end, okay. And so we're gonna make a hardness test here, 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 the whole length, really, and it'll be spaced. The spacing is to be roughly 1/16 of an inch. Spacing, and we do this all the way to the end. All right, in other words, and that's where we're going to be taking our hardness readings every 1/16 of an inch. All right, so when we're doing that, we can see that, and then of course I forgot to put that little expanded section, the head on this thing, which I can't draw very well, but anyway, that's the head of that up here. Okay, so when we're taking this and we're plotting this with respect to the HRC, and then this is going to be, at the bottom is going to be distance from the quenched end, distance from quench in. All right. And we're going to plot that. Okay, so let's see. I'm setting up something here. All right, so distance from the quenched end will be represented down here. And we won't put actual marks on here. But you can imagine that, depending on what alloy this is, of course, depending on what alloy it is, we're going to have a curve that begins to sort of simulate something like this. With this being, let me put some values here. Let's say this might be, and this is 60, which is very hard. And then we could come down here to 50, 40, 30, 20, something like that. Okay, so once we start taking those marks, and we take them, like I said, every 1/16 of an inch, the curve starts to look like this. Slowly, slowly, slowly falls, and then kind of starts to level out. Once it gets towards the end, it's basically completely cool, so it starts to flatten out a little bit. Okay, so this is the essential geometry of this curve. Now, what we're looking for, and I'll show you some examples there. The steeper this curve is, the drop, really the less hardenability it is or has. All right, but the flatter this becomes up here at the top, if this is more flat towards the top, then that means it has a really good hardenability rating. All right, it has a high hardenability, because even though you may be an inch or 2 inches from that quenched end, you're still getting a fairly high. If it was more something like this, which I'm going to give you some examples, but if the reading was more something like this and then fell off, you can see this has much higher ratings farther down from that quenched end. So you can rate these two steels, the red and the green steel, as far as its hardenability ratings. This would obviously be have a greater hardenability capacity to it, this particular alloy, the green alloy, as opposed to the red alloy here. All right, so now I want to also show you kind of what's taking place with respect to on that diagram, on the IT diagram, and how it referenced. And so I have this diagram here that I wanted to show you, but I'm going to have to refocus the camera here. Okay, so here's what we've got, and I wanted to show this to you because it kind of puts it in perspective. But again, here's this quenched end right here, and this actually, if you look at it, this actually is part of that S curve on the diagram, that on the IT diagram. This is the beginning of that S curve. And normally it would come down here. This would be the nose, and it'd come down here, and then kind of look like this and flatten off. Now, this line from here all the way across, this dashed and dotted line here, that represents martensite start. Okay, so what this is showing is very close to the end, right here at A. This is point A, right here. Look at this. Here's the curve. It completely misses the nose of this. So you would think, sure enough, it comes down here and goes completely into martensite. So this is a 100% martensite structure. You can see that here because it misses this curve. It's not showing the other part of the curve, but you really don't need to, because this is just showing the apex of that curve. This is the nose, that paralytic nose here. Okay, look at part B. Point B is just a little bit away from that, maybe maybe a quarter inch. Well, actually, about a quarter of an inch, because this is half an inch right here. And look what happens. The farther away it starts to hit that paralytic nose and actually goes in here. So you're going to get some perlite, and then it keeps going, and comes down here and finishes in martensite. So part B is going to have some perlite, but the lion's share of it will still be martensite at this point. Okay. Now C is way down here. C is half an inch away. All right, and that's associated with this curve. And you can see easily that it starts in perlite and finishes in perlite. So it is a, well, they're calling it a fine perlite. We didn't differentiate, but that's on the higher end of that. This is a fine perlite, whereas this other one at 2 inches away, way down here, and it's just a standard perlite, okay, or what we call it coarse perlite. So I just kind of want to show this to you, how it references the IT curve, or the time temperature transformation curve, with respect to the results from this Jominy in Quench test. So obviously, if at this point right here, C was still missing or getting just a little bit of this, we would have a much flatter curve here, and which would mean this particular alloy, had it been that way, and missed this and not gone into 100% fine perlite, we'd have had a much higher hardenability alloy, something compared to that maybe. So this is a really good description of what actually is taking place with the Jominy in Quench test and the IT curve. IT. All right, now this will kind of, I've got a picture of this because I kind of want to show it to you also. But this is the actual apparatus. This is the one we have in our shop, all right, or in our lab, and it's very similar to this. And I'm really sorry that y'all didn't get a chance to really use this, but this is essentially what's taking place. Here's that fixture. Here's that piece, the specimen being held in place here. Here's the water nozzle hitting the bottom of this thing, and then the water just, goes in here, then drains out. So that's the actual apparatus for this Jominy in Quench test right here. I wanted to show that to you briefly. And let's see what else I got for you here. Okay, well, this is just another showing that same kind of curve, standard curve here, you can see. Now this is the one I really wanted to show you, because it really gives you a change, shows you the change. And again, I've got this as about as high as I can get it. Okay, now this is what I was talking about a moment ago. This makes several points. All of these are 0.4% carbon in them, because they're all, this is a 40, this is a 40, this is a 40, so that reflects a 0.4% carbon content. Now look at these first two numbers from our AISI, American Iron Steel Institute designation. These first two numbers are the major alloying group, and so this 10 represents a carbon, and this 4340 represents a chrome moly, chromium molybdenum. Now, as I told you earlier, those alloys, the chromium, molybdenum, etc., really elevates the hardenability of these steels. And so you can see that right here, because here's the distance from the quenched end, yet look at the reading almost all the way across from one end to the other on a very high Rockwell C scale. So it is a very hardenable steel, 4340. Now the 3140 falls off a little bit. You can see here the hardness rating comes down, falls a little bit, but this not as bad as the standard carbon 30.4% steel here, the 1040 steel. You can see it falls off rapidly like this. So this is a really good explanation, or showing the difference between these different alloying elements and what it can do for the hardenability of these, based upon the wonderful Jominy in Quench test. Okay, so all right, I think that will do it with respect to hardenability. It's something you need to be aware of when designing apparatuses and components, knowing if a steel has the chance to be hardened, and if so, how difficult it might be, based upon those factors I listed on the first video. Those three factors being the composition and the quenching media, and then the actual last one was the size and shape of it. Okay, so keep that in mind, and we will be back later. Thank you.